Okay, we're gonna continue the lecture on the measures of position where I stop in the class, which is in this example number 2. So I said before in the class that this is the record of one of my stats class students, 24 of them, their height in inches, and I put male and female together. So I was asking them how tall they are. So the first number is 65. They will be 5'5", 65 inches, right? 72 inches will be 6 foot, and so on. So we have all of those numbers that are recorded heights of the students in inches. So to make it easier rather than complicate with foot different measures. Okay, so you can sort this data, and again, if you sort this data by hand, you're gonna have to go throughout to find the smallest thing, 45, or the biggest thing if you want to sort from the top down, 85. You put 85, cross 85, the next biggest thing, and so on, and keep on crossing like that. It will take shift display, which we were discussing in the one of the previous lecture. Or you can just simply use your calculator. Now if you have a calculator, so you turn your calculator on, you go for statistical feature in your calculator, edit, and you put all of the data in your calculator, and then this is already sorted, but I have at least 5 already sorted, these numbers. But if you don't have it sorted, then you go and sort. You move the arrows, the sort in ascending order, sort in descending order from top down, or in ascending order from bottom up. It's up to you. Let's sort it in ascending order. If I sort it in ascending order, it will be the smallest first, and then the least 5 second, least 5 on the bottom 5, close parentheses, enter, and now they are sorted. And you go and take a look and edit again, stats edit option, and you can see 45, the smallest one, 50, the next one, 52, and on. Okay? So one way or the other, you're going to sort them somehow, right? Now, why do you need to sort them? Because obviously you need to find the minimum and maximum. If we are talking about a 5-point summary, we are looking for the minimum, for maximum, for median, for quartile 1, and for quartile 3. So we said the minimum and maximum is going to be very easy to find out once the data is sorted. So in this top-down sorting, I have descending order, right? I have 85 the top maximum, 45 minimum. If I need to find the median, I'd be looking for the middle value, which I don't have here because the sample has 24 things. So it's naturally divided in 12 top values and 12 bottom values. In which case you have the smallest one in the top half and the biggest one in the bottom half, and the average of these two, 66 and 65, is the median. Median is 65.5. Okay, you can find the average of two numbers easily, right? Now you look at the quartile 1 and quartile 3 remaining feature. That would be the median of the bottom half for the quartile 1 and the median of the top half for the quartile 3. So the quartile 3 is bigger than the quartile 1, of course, and the median is in between, right? So what happened in the bottom half, I have also 12 even number, so I have 2 in the middle, 62 and 61, these two, right? You can count, right? 12 things, what's a half? 6. So the 6th and the 7th are the 2 in the middle, and therefore this will be 61.5. And the same thing in the top half, I have a 72 and 71. The average is 71.5. That's a quartile 3. So now we have a quartile 3, we have a quartile 1, and we have a median 65.5. Obviously, we have a minimum and maximum 45, 85. I present that this way. I said it in the class that you can also separate them with a comma. Anyway, you need to have a minimum, you need to have a quartile 1, you need to have a median, you need to have a quartile 3, and you need to have a maximum. When you have those 5 numbers, they are called 5-point summary of the sample. This is 5-point summary of the sample. What we do with that is we create something called box and whisker diagram. This is also called box plot. So there is another name for that, box plot. Obviously, this is a graphic presentation. Okay, so this is colloquial name for that, box plot. But the proper name would be box and whisker diagram. Okay, that's a box and whisker diagram. What do you do here? You need to have a scale. So you will need to have a scale. They're probably going to be something like 40, because the small piece of data is 45, of course, right? So you have 40, you need to have, I guess, my scale here. The scale would be the first thing you do, right? Rather than, you know, the box and whisker diagram. Of course, this picture here is just straight out of computer, so it's much easier to do that if you have a computer. 50, 60, and then it would be, I guess, 70 here. See, my scale is really lousy here, all right? What I'm doing right now, of course, the scale on the box plot above is just fine. 80, and I guess you would probably need to have 90 just to make sure that you get 85 right in the middle. Okay, and then you start working on the thing. You will have the left tail. This is not necessarily to be anything large here. You can just have a dot if you like, you know, something like that. I might even have a cross. Okay, and then you need to have a tail goes up to the first quartile. First quartile should be 61.5 in your scale to be somewhere here. Then 65.5 is the median. In the middle of the box closes. So this is a box. Central, 50% of the data between the quartile 1 and quartile 3. The middle, 50% of the sample is here. And the box closes at 71.5. And then you do the box. Median ought to be a vertical line somewhere in the box, because it's going to be between quartile 1 and quartile 3. It could be closer to one of them, it could be in the middle, it could be closer to another one, depends on the sample. And then you have another tail here that, again, you can have the vertical line here, vertical line segment, or you can just simply have a cross or a dot. And then you have the maximum, right? So if I do that by hand, this is how I do that. So I have a 45. Okay, I have a 61.5. I have a 65.5. I'm simply repeating out of my memory what was the 5-point summary. I have 71.5, and now I lost it. Yeah, I remember well, okay. 71.5, and I have 85, okay? So if I want to create box plot, I will have the scale. You definitely want to use a ruler, right? I could use a ruler here, but I'm just simply going to do that. I do a sketch here. So I want to have 40 because I know I need to have something below 45. I need to have 50 then. Continuing with 60. I have 70. This is not a box plot. This is just a scale. 80. And 90. And that's going to be good enough. Okay? So now I want to create a box plot. 45 is somewhere right in the middle between 40 and 50. That's the beginning of the tail. It goes to 61.5 at the box open. So it's going to be approximately here. This is where the box is going to be. Then the box closes 71.5. So something like here. Okay? That's the box. Quartile 1. quartile 3. You could write the numbers here on the top of that, but we don't usually do that. 65.5, 65.5 is somewhere like here. So it's closer to the quartile 1. Okay, and now I'm going to connect the minimum with the box. Okay, and I have 85. 85 is right in the middle here. So I'm going to do another tail here. That's the box plot, sketch of it. The proper one should be really done with the ruler so that it looks decent. It gives you some idea what the data is. So this is central 50% of data is fairly condensed here. There is quite a big, large difference from the quartile 1 to the minimum, and the same thing goes to the maximum. So this 25% of the data is spread more than this 50% of the data, obviously, of course. It's even spread more than this 25% and this 25%. And this is even more, there is more variety here than here, what I see from the sample. So give me some idea about distribution of the data, right? It's not a histogram. Histogram is much better, but it gives me some idea. I would say this is skewed to the left, or it's what is usually called negatively distributed. Left negative, right positive. So that kind of question in the homeworks, you know what it is about. But I would really not want to characterize this because the tail is negatively distributed or skewed to the left, but the first quarter is actually shorter. Second quarter is actually shorter than the third quarter. Second quarter is shorter than the third quarter. So there's more. The histogram, what I would expect, would be more skewed here than on this side. So I don't really know what it's gonna look like. Okay, this part here is less pronounced than this part here. Okay, so all right, but that could also depend on only one item. So let's go back and see this a little better graph here. What do we have here? You can also do the same thing with your calculator. Your calculator can do the box plot. So if you do the plotting, you need to go for statistical plot. So second statistical plot. Oh, I forgot to turn it on. Second statistical plot. Oh, I did something else. Second statistical plot. All right. I'm gonna quit this. All right. Second statistical plot. Let's put the plot on. And it's on already because I was doing some histogram before, and I want to use the type that is a box plot. Now this is a box plot with outliers, this one here. I don't want to do that right now. I'm going to explain it in a moment. This is the one without outliers, just a box plot. It looks like a box plot. The data that I have, I think it was a list 5. Okay, and I don't have a frequency list. And now graph. Let's try again. All right. Quit. Let's try again. What was the problem? Let's see. Oh, I think he wants me to do the one here by default. Every single piece is once. I hope this is okay. So I'm gonna have to do the box plot again. Okay, I selected that, and the color is gonna be blue. That's fine. Let's graph it. All right, looks great, right? And make sure that your data is a proper window. Now, you don't have to do it like histogram. You have to start with the minimum and then maximum. No, you don't have to do it that way. But you need to have the data ought to be going from 40 to 90. So maybe the X minimum should be 45 is the smallest thing in the sample. Should be probably 40 to make it nicer. And the maximum should be probably 90, or maybe 100 is okay. I don't know. The scale is not needed really. I am going to use a scale 5. I want to have 40, 45, 50, 55. Those are notches on the bottom or the box plot. This is different than a histogram, so it's not the same story. So I think it's going to look a little nicer here. The y minimum, y maximum is totally relevant here. The box plot could be clever. You just don't want to have it on the x-axis, because in that case you're going to have a line through it. And okay, the box plot, some people do box plot like that. Nope, you don't do that. There is no any fishbone here, okay? So don't do that. The box plot has only vertical lines in the box, okay? No horizontal lines in the box. So don't do any fishbone. People do that sometimes, and it's really not what a box plot should have. The box plot also could be vertically positioned. So this thing could be up, the tails could be this way. That's another way of doing it, and you probably on the internet to see the box plot that is in a vertical position rather than horizontal. But I'm going to use a horizontal position. So I adjusted this window so I can graph it again. Looks slightly better, I think. I don't know. Okay, now you can trace it, and the trace will reveal the minimum, maximum, quartile 1, 2, 3, and median. Okay, it starts with median 65.5. You can see that, and you can move here, and now you have 61.5. You can move here, and you have 45, and it gives you maximum and also quartile 3, right? So you can see that. Again, the option for statistical plots are that you can only do that horizontally according to this, right? And really the only other option you have is you can use a blue color or you can use a red color, and then you have to select that with the arrows, right? And the arrows are here on the screen, so you have to go red, and that's it. I mean, there's really not much options basically, but that's pretty much the same what I have here, right? And this is nicer, I think, because it's bigger at least. Okay, what about interquartile range? Why do we need to know interquartile range? Well, first of all, interquartile range. Interquartile range. The difference between the quartile 3 and quartile 1, in this particular case, 71.5 minus 61.5 is 10. Okay, that's where the central 50% of the data is. So you can say the 50% of the sample, the central 50% of the sample is here, between these two numbers. So it's fairly compact, okay? And if I divided my sample of the female heights and the male height, it would be even more compact. People don't differ that much in height, adults, okay? So not surprised here, okay? But there's another reason why we want to have the interquartile range, and that is to find outliers. We use interquartile range to find outliers. Here's the definition. You can say, oh, I'm looking at this sample, this guy's an outlier, it's too short, and this guy is really too tall, so he's an outlier too. Okay, that's an opinion, okay? We have a definition of what an outlier is, and this is what you have to do. You have to use the interquartile range. So you're gonna say 71.5. That's the quartile 3 plus 150% of the interquartile range. So you're going to multiply interquartile range with 1.5. Now in this particular case, that's 10. Okay? Now you find out what this is. So this is 15 plus 71.5 is 86.5. Anything above that is an outlier. So basically, you are using interquartile range, 150% of that, 1.5 added to the quartile 3. And that ends up everything outside of that range on that top side is an outlier. We don't have an outlier here. This guy is not an outlier. So on this side, we don't have an outlier. On the other side, we might have an outlier. We'll check it out. But you need to do the same thing here. Only you're going to use a quartile 1, you're going to be subtracting 150% of interquartile range. So you have a 61.5, which is a quartile 1. And now you're going to subtract. Again, the same thing. 150% of interquartile range, which is 10. And 150% in terms of decimal numbers is 1.5, right? So this time, you're going to subtract 15 from 61.5. and that's 40, in this case 46.5. Okay, now 46.5 is a boundary for the outliers, so that would be something like here. Okay, so this guy is an outlier. Is there anything else? This guy is an outlier. 45 is below the boundary for the outliers, 46.5. This guy is not an outlier. It's not beyond that boundary. Below, this guy is out. So the rule is very simple. If you are looking for outliers, it will have to be 150% above, more than 150% above the quartile 3, or 150% below the quartile 1. So how do you get those boundaries? Well, find 150% of interquartile range. In this particular case, that is 10, and 150% is 1.5. So you multiply, that's 15, and add to the quartile 3, or subtract from the quartile 1. If something goes beyond those two boundaries, or below in case of a lower one, above in the case of the top one, those pieces of data are outliers. So there is only one outlier in the whole sample here, and that's 45. 85 isn't outlier in our definition of outlier. So you need to remember that. So again, the calculation is find the interquartile range, which is 1.5 of interquartile range, to the quartile 3, and subtract from the quartile 1. Those are the boundaries for the outliers. Passes those boundaries, those are outliers. If it doesn't, you can also find it in your calculator. So the calculator will tell you, now this is the box plot with outliers. So this time, this one, but we're going to do this one. This is the box plot with outliers. What's the difference? And it says, it offers you what mark. Just use the first one, or this here. So there is one more option here. We can use a different mark. So we are going to graph this. Here we go. Okay. One more time, you can trace the stuff. This time starts with the 50. That's the first part of the sample that is not an outlier. From the bottom up, 50. Then quartile median, quartile 2 median, quartile 3 maximum. Minimum is still the minimum. 45 is still the minimum. You cannot change the minimum, but it's also an outlier here, separated from the tail here. The outlier could be separate from the tail on a box plot. So the tail will start with the 50, not with 45, if you want to emphasize outlier. And anything that is an outlier would be a dot. There might be another outlier here, might be another outlier here, so on. Okay? That's how it's going to look like. We're not going to really emphasize box plotting with outliers. It's usually not done, but you could. The idea for an outlier is anything that passes boundary that is a quartile 3 plus 150%, 1.5 of the interquartile range. Formula. Anything that passes that is an outlier. Anything that is bigger than that. Anything that passes the lower boundary, which is when you subtract the same thing here from the quartile 1. So you subtract 150% of the interquartile range. Then you get a lower boundary for the outlier. Anything that is below this boundary is an outlier. Okay? So outlier is any piece of data in your sample that is above a boundary above the top boundary for the outliers or below the bottom boundary for the outliers. Okay, so that's the formula. It's kind of like I don't really have a formula because the piece of data could be either above this or below that. So, but that's the idea. Okay, so these are the formula. Find the boundaries this way. Okay, that's how we know when somebody says this is an outlier in the data. That means it is beyond that boundary for the outlier. Okay, and I know people use sometimes colloquially the term an outlier. That doesn't mean anything really. It's their own opinion. We do not, again, if you look at the data, you can have an opinion, oh, 85 is here, because it's 10 more than 75. So it kind of like looks like outlier. This guy might not look like outlier. It's just 5 below 50, so it's not that far. But it is. This one is an outlier, and this one isn't in our definition. So we have a formal definition of what an outlier is, okay? And again, box plot could be graphed with the outlier. So what will happen here, that this guy would be specially marked separately, and then the tail would start at 50, and then we would have the rest of the box plot the same. If you have an outlier on this side, it would be the same story. Okay, z-scores. Now this is also important. Now the z-score or z-value, right? Z-score is sometimes referred to the z-value. The meaning of that is a numerical reference for the distance of a piece of data from the mean in terms of standard deviation. So if I tell you that the height of American male is 69 inches on average, that would be the population mean, and the standard deviation is 3 inches. Okay, now I can ask you, what is your height? Let's say you're a male that is 6 foot tall, so you say I have 72 inches. That means you are 3 inches above the average, which is 60, what I said, 69. 72 is 3 inches above that. And that's exactly standard deviation. Your z-score, your z-value would be 1. Your z-value of your height would be 1. Because you're 1 standard deviation above the mean. If you're 2 standard deviation above the mean, your score would be z-value. Height would be 2. If you are 1 inch above the mean, the z-value would be 1/3, because you're 1/3 of a standard deviation above the mean. If you're 3 inches below the mean, if your height is 66 inches, so the average height is 69, I said 69, could be something else. The average height is 69, 66 would be 3 inches below. So if somebody is 66 inches tall, the z-value of that height is -1, because it's 3 inches, 1 standard deviation below the mean. Okay? So I'll give you a lot of talk, but there's a formula. Z-value is calculated by taking the x value, whatever that is, whatever your height is, minus the mean. In case of sample, mean of the sample. In case of population, mean of the population. And then you divide it with standard deviation. Again, in case of sample, sample standard deviation. In case of population, population standard deviation. And that's the z-value. Okay? So again, in case of a population, it's the same formula, only different labels. So we have the x, the piece of data that you're interested in calculating z-value of. You subtract the mean, you divide with standard deviation of the population. So this is not going to be the same number. It will depend whether it's a population or sample. But the formula is the same. Piece of data minus the mean divided with standard deviation. Piece of data minus the mean divided with standard deviation. In case of sample, sample stuff. In case of population, population stuff. Okay? So I have this heights of those students, okay? So I calculated that the mean height of this group of students is approximately 65.29 inches. So I'm using 2 decimal approximation. And the standard deviation, sample standard deviation, I'm using this group of students, so 24 students, as a sample of the students, say, in Suffolk County Community College. And in this sample of 24, the sample standard deviation is 8.83. And again, for the people who have a problem how to calculate it by using that table when you do the x's and the x squares, which is really not that hard, but if you have that problem, you can use a calculator. And in the calculator, I need to quit the screen and clear the rest of that. You go for stats, you find your data. If you don't have it, my data is in the list 5. If you don't have it, you have to put it in. And then you go back to the stats, calculate. One variable calculation, the data is in list 5. Frequency list, this is funny stuff. In here, I don't have to put anything, but when I do the box plot, you have to put 1 there. All right. Anyway, and then you calculate. Beautiful. Now I have here 65.29. That's what I approximated. You have to cut all those digits or unless you need more decimals. And the sample standard deviation, I said this is a sample, so it's a sample standard deviation I'm interested in, is 8.83. Okay, approximation. Okay, population standard deviation will be 8.64. I warn you about it, that population standard deviation is going to be different calculation than the sample standard deviation. And population standard deviation is always smaller because you're averaging with 1 more. Okay, if you look at the formulas, all right, it's always going to be smaller than the sample standard deviation. But of course, for population, you calculate population standard deviation. For sample standard deviation. You could definitely ask the question why. The answer is theoretical, so we're not going into any advanced probability or statistics, so we're going to leave that outside of our class. But there is a reason for that. Okay, so now the z-value. Any of these guys have a z-value. Well, let's say 75. I'm interested in the z-value of 75. What's a 75? Well, the question is, how far is it from the mean in terms of a standard deviation? So, formula for calculation is this one here. Okay? The piece of data I have is 75, so that's the x. Minus the mean, which is 65.29. Divided with the standard deviation, which is 8.83. So I'm just plugging it into the formula. And I'm getting the z-value of 1.1. Which means this guy, 75, is 1.1 standard deviation away from the mean. Above the mean. Okay? Let's go and calculate another one. Z-value of data entry 52. That will be this guy here. 52. Okay, the same formula. 52 minus the mean divided with standard deviation. So I have it here. 52 minus the mean, 65.29, divided with standard deviation, which is 8.83. My calculator, so you basically need to calculate this with any calculator you have. Negative 1.505. I'm using 3 decimal here because the 3rd decimal is 5. I don't really want to round it. I just want to keep it this way. Okay, so which means the data entry 52 is 1.505 times standard deviation lower than the mean. Okay, the negative means lower than the mean, negative z-value. Above the mean, positive z-value. Okay. Now these z-values are the values that we will be using in any so-called normal distribution. So you need to remember this stuff when we get to that point that we're going to be using. And again, z-value for the samples calculate one way, z-value for the population calculate another way. I have to say the z-values are mostly calculated for population, not for the samples. But you can calculate for either, right? It's kind of a strange thing to say, because we said that standard deviation is usually calculated for the sample, not for the population. But it can be calculated for population as well. While the z-values are usually calculated for the population, not for the sample. But the formula is the same. The x value, whatever the data value is, minus the mean, or whatever the mean is of sample or population, divided with the standard deviation. Sample, standard deviation in case of sample, population, standard deviation in case of population, right? And you will get that value. What it's telling you is telling you how far away. So you have the mean somewhere, the z-value is 2. It tells you that that data entry is 2 times standard deviation above the mean, okay? If it's 2. If it's minus 2, then it's 2 times standard deviation below the mean, right? To give you some idea where it is in terms of standard deviation, not in terms of a position in a box plot, but in terms of standard deviation. Okay, you can go other way around. So, for example, if I give you the z-value to be 1.1, I already know that's this. In this particular case, that's a 75 has a z-value 1.1. Then what you do to get the x value, so you have the z-value. To get the x value, you multiply the z-value with the standard deviation, and you add that to the mean. So that would be z-value 1.1 times standard deviation 8.83, added to the mean, which is 65.29. So 65.29 plus 1.1 times 8.83, and you get 75, right? So there is one formula that we calculate the z-value. If you solve this formula, you get the x value from a z-value by using this formula. So the mean, so people that know algebra will notice what I'm doing. If you don't, you just remember formula or have it written somewhere. Plus the z-value. You might ask the question, why is it called z value? Why just not something else? Well, this is connected with a label for the normal distribution, which we use z for that particular purpose. But we're gonna get to that point. Don't worry about it. All right. I need to put a standard deviation here, so I already messed up. So let's see. Okay. So that's the formula to get the x value out of z value. This is the formula to get z value out of the x value. Right? The x value 75, the z value 1.1. To get the x value 75 out of z value 1.1, you use this formula. This is basically the same equation as this one, only this one is solved for z value and this one is solved for x value. And we don't write x value, we just write x. Okay? The same thing here, only different label. The mean for the population is labeled Greek character m, or Greek mu. Z value is still the same. If your algebra is good, you don't need to have any of that. You can just simply solve the equation, this equation for x. But here it is. Okay, you want to calculate the x value out of z value. You multiply z value times standard deviation, add it to the mean. Now these are the labels for the population, right? Population mean, population standard deviation, and you get the x value. Okay, how to get a z value out of the x value, how to get the x value out of the z value. Of course, in both cases, you need to know what the mean is, and you need to know what the standard deviation is. So your sample or a population need to have the mean and standard deviation. It will have it. It's just a question about whether you know what it is, right? So you're going to have to calculate. Okay? That's my story. I have some extra homework here, so I kind of, if you don't have enough homework on the Connect Math, you can play with this. Here's the Hawaii airport luggage example we had some time ago. Find out the 5-point summary: minimum, quartile 1, quartile 2, quartile 3, maximum, quartile 2 or median, right? Sketch and box and whisker diagram. You see if you can do that. Now and I'm asking here, can you find the percentile rank of the data entry 38? 38 is this guy here. Can you find the rank? Not percentile rank, just rank of the data entry 29. Now, I didn't tell you what's my optimal case here, right? You can guess. I want to have as little luggage as possible, so I want to do that in ascending order. It's up to you, right? So if you don't have the preference, go in ascending order for the rank. Percentile is always the same. I had to be one particular way. What is it's always in ascending order. It's what is below. The lower percentile is down, the higher percentile is up, right? And do the same here for NFL players. You can try the same. Again, I divided the sample into 2 equal parts. You can easily find the median. I think we did it some time ago. And then you can easily find the quartile 1 because you just have to find the average of these two guys. The quartile 3 is the average of these two guys. And of course, you have the minimum here, you have the maximum here. Try to make a box and whisker diagram if you can do that nicely. See if you can do it nicely. Okay, and then another question here is the data entry 32. This guy here. What's the percentile of this guy? How many are younger than he is, right? That will be the percentile. What is the rank of the data entry 30? So that's this guy here. What's the rank? So now again, if you don't have a preference rank, you can go in ascending order. So that would be default. And I also have something else here. Maybe you want to do the United Nations child infant mortality rates. You look at that. It'd be an interesting thing to see the box plot there. Or 5-point summary. I'm not asking you. You don't have to do any of that. If you don't have a time, make sure you do the homework on Connect Math, because that's not an optional. It'll be graded. Homework is 30% of the total grade. Not this homework, all of them combined, right? All of them are equally of equal value. Okay, that's my story for this lecture, and this lecture will be posted on the YouTube into perpetuity. So you are welcome to view it anytime you want. Okay.